empty if provided I can produce a good quotient, which I called J sharp of P, or was it maybe J0 sharp of P, I called it, which was a quotient of J naught of P, and it had to satisfy two conditions. One, that it has finite Mordell-Weil group, that's a substantial one, and then a kind of other, is more geometric local condition, that the natural map from J naught of P to P to J naught of P sharp is a formal immersion at the point infinity. So if we have those two things, so there's just a good quotient, so we want that J0 sharp P of Q is finite, and we want to have formal immersion at infinity. And then we saw that if we have these two properties, we can conclude that there are no rational points on Y1 of P. So now the order of business is to understand enough about the Jacobian of the modular curve x naught of P, the Jacobian J0 of P, in order to produce such a good quotient, such a quotient with finite Mordell-Weil group. And the reason why we can do this, generally this is a very difficult problem. I mean, if you're just handed an abelian variety or a Jacobian of a curve, it's very hard to understand, even to compute on a computer, it's a Mordell-Weil group. But here we have a lot of control on the situation thanks to the connection between J0 of P and its various quotients and modular forms. So at the end of the lecture this morning, I introduced the space of modular forms, which I denoted by S2 of PR, which were the space of regular differentials on the modular curve x naught of P over R for R any Z algebra. And we saw that this could be embedded in the space of power series in Q by taking an expansion ad infinity, and the fact that this is an injection is known as the Q expansion principle, that a modular form or a differential is completely determined by its Q expansion. Okay, so this space of modular forms corresponds to the tangent space, to the Jacobian at the origin, and so one can kind of study various structures on the Jacobian by looking at what they do to these spaces of modular forms. Now, another crucial ingredient that we have in understanding this Jacobian are the so-called Hecke operators, which are special endomorphisms. I mean, the idea is that we want to break up J0 of P into irreducible pieces by using the action of the endomorphism ring or the endomorphism algebra of this abelian variety. Now, in general, abelian varieties, I mean, I don't know, tend to possess very few endomorphisms, but for these ones, they have a remarkably large ring of endomorphisms coming from certain canonical correspondences on the modular curve. Now, where do these Hecke operators come from? Well, if you look at x naught of P, so if you take the modular curve x naught of P, it's equipped with two maps, and if I take a prime L, let me suppose to simplify that L is a prime not equal to P, then I can look at the modular curve of level PL, and I have two maps from x naught of PL to x naught of P. Okay, because if I can think of this as being an object consisting of classifying triples, consisting of an elliptic curve, a subgroup C1 of order P, and a subgroup C2 of order L. Okay, to give a group of order PL is the same as giving yourself a group of order P and a group of order L. Now, this map I can associate to this E. I can just forget about C2. But I can also do something else, which is to sort of mod out this whole, these first two pieces of data by the group C2. So I can look also at E modulo C2, which is a curve defined over the same base, because C2 is defined over, and then look at the image of C1, C1 bar or something, the natural image of C1 in this, which is, of course, still of order P. So you have these two maps, and so this gives rise to an embedding of the curve x naught of PL into the product of these two modular curves. It also gives rise to a correspondence, which, so if I have a degree 0 divisor on the curve, I can look at its inverse image then project that back down to the other factor, and that gives rise to an endomorphism of the Jacobian. Okay? So this correspondence, which is commonly called TL, gives rise to an endomorphism of the Jacobian J0 of P. And the description I gave, I mean, everything here is defined over the rationals or over Z even, okay? And so, well, it's Z1 over L, I guess, if it wants a smooth. So the corresponding endomorphism is defined over the rationals as well. So it gives rise to an endomorphism of J0 of P. So this TL belongs to the ring of endomorphisms of J0 of P, which are defined over Q. So I can look at the subalgebra of the endomorphism ring, which I'm going to denote T. So the subring of end Q of J0 of P generated by these Hecke operators, T sub L. And now we would like to, so here I'm just going to take primes L not equal to P. And we would like to understand something, to say something about the structure of this Hecke algebra acting on J0 of P. So this is sometimes called the Hecke algebra. So, okay, so claim, so maybe, so what do we know about T? So T, maybe let me say T tensor Q. So T is a Z algebra. It's of course finitely generated as a Z module, so it's certainly finitely generated Z algebra. Let me look at the corresponding Q algebra. So T tensor Q is a semi-simple commutative algebra over the rationals, and moreover I can say something about its dimension. The dimension over Q of this algebra is equal to the dimension over Q of the space of modular forms of weight 2 with rational Fourier coefficients, so with rational Q expansions, and it's also equal to the genus of the modular curve x naught of P. Okay, so this equality is just the fact that we know that the genus of a curve is the dimension of the space of regular differentials. The beef here is this one, that these two spaces have the same dimension. So this gives me a good idea of what the ring of Hecke operators looks like. Okay, so this is the only proof I'm going to give. I'll give you a little outline of that. Why is that? Well, the key to this is the fact that there is a perfect pairing from the algebra T, tensor Q, and between that and the space of modular forms of level P and weight 2. So we have a natural bilinear form which takes an operator T and a modular form F and sends that pair to the first Fourier coefficient, the A1 coefficient of the form TF. So I apply T to F and I look at the first Fourier coefficient. Yeah. Oh, where my maps here? Yeah. So maybe yeah, here it's a little bit unreadable. So here I'm modding out. So this is a group of order L. Sorry, order P. And this one is of, and the second is of order L. So C1 is of order P. C2, the middle one, okay, slide it up a little like that. Huh? So I shed some light on this line. So C1 is of order P, C2 is of order L, The first map, I just forget about C2. The second map, I mod out by C2. I take the quotient of E by C2, and I look at the image of C1 in that quotient. Those are the two natural ways that you would, if you were given this, if you were handed this triple, how you would construct. So there are these two different ways. So if you think about what the correspondence does, it's actually, I should maybe have said, this T is of by degree P plus 1. And so you would start with a degree 0 divisor, and you would get something of degree P plus 1 times, you would get a, this A1, this is the first Fourier coefficient. So I take TF, I write it as sum of an q to the n times dq over q. Okay, so this is a differential, so that's a q expansion. I write the q expansion like that, and I pick up the first coefficient, the coefficient of q. In that expansion, that's my A1 term. That's what I call A1. So I take A1 of TF. Now, it's clear from that definition that this is bilinear. Okay, I mean, it's a bit of a challenging exercise because I haven't had time to give enough background. But I'll leave it to you as an exercise to think about. Those who know more about modular forms and Hecke operators will be able to do this exercise very easily, and maybe you can explain to others how to go about doing that. Exercise, show that this is perfect. Excuse me? What? Because of the Q expansion principle, okay? So these forms are, I start with a modular form. The point is that the Hecke algebra T operates on S2PQ. It preserves the space, okay? Because the Hecke operators are defined over Q, they give rise to endomorphism, the Jacobian over Q. So they send differentials defined over Q to differentials defined over Q. So it's a consequence of the Q expansion principle. So show this is perfect. So that's basically the idea is that a modular form is determined by its Fourier coefficients. That's the key to that exercise. Okay, and once you, of course, by duality, once you know that, then everything follows. Yes. Either is fine. I don't really care. If you're happier, of course, the dimension over C of the space tensor over C is going to be the same. So, yeah. But I mean, this is perfectly fine. Heck, everything preserves the rational structures, right? So, I haven't taken eigenforms yet, so I'm not worrying about. These are just rational vector spaces of the right dimension. Okay. So. Okay, so now, what do I want to say? Yes, so corollary of this basic structure result is that we have a fairly good idea of what the Hecke algebra looks like, at least tensored with Q. T tensor Q is isomorphic to a product of fields, which I claim are indexed by the algebra homomorphisms of the Hecke algebra, right? So the product of KFs as F ranges over what are called normalized eigenforms. So why is that? So a normalized eigenform, I'll explain also what KF is. So KF here is the field generated by the Fourier coefficients of F. Yes, it's completely explicit. You can write down a formula for it. Maybe I should have mentioned this also, because that is also a way of seeing that somehow what I'm saying here makes sense, right? So TL, if you look right on the level of Q expansions on the space of forms of way 2, there's an explicit formula. This is the sum of a n over L Q to the n over all L dividing n plus L times the sum of a n Q to the NL. So we had this completely explicit formula for the action of the Hecke operators, which shows that if I start with a form with rational coefficients, I'm going to still have rational coefficients. And this is also a fun exercise. A bit challenging because I haven't had time to really go into details, but this is essentially elementary once you get all the definitions right. No. Yeah, that follows from semi-simplicity, but provided you pass to a sufficiently large extension of the rationals. Okay? So over the complex numbers or any algebraically closed field, yes. But that's what I'm going to say here, actually. I'm going to get to that now, actually. So what do I mean by this? Okay, but what do I mean by normalized eigenform? So an eigenform is a modular form which is an eigenvalue, which is an eigenvector, which is an eigenvector for T, a simultaneous eigenvector for all the Hecke operators. So, of course, in order to diagonalize these Hecke operators, I might need to pass to an algebraic closure. So maybe F belongs to S2 of P with coefficients in Q bar. But, of course, a finite extension will do. I have a collection of G by G matrices, and I just make an extension which is large enough to diagonalize them. And then the other thing is that if I write F as a sum of an q to the n going from 1 to infinity, that's the Q expansion of my eigenform, and here normalized means that A1 equals 1, then I can recover the L Fourier coefficient as the eigenvalue of TL. Eigenvalue of TL acting on this F. Now that is a consequence of the explicit formula that I gave here for the action of TL. So if F is an eigenform, you see that the A1 of this new form is AL. Okay? So that means that you can recover the form if you know the system of associated Hecke eigenvalues. Yes, this was a space of regular differentials on the modular curve, on the complete modular curve on x naught of. So it's really cusp forms, yeah. Yeah. I'm not going to talk about Eisenstein series. Maybe Marussia will say, I don't know. So, okay, so now I can, given that I have this decomposition, okay, so of course T then is an order, okay, it's a finitely generated Z submodule, as a subring which is finitely generated as a Z module in this product, in this KF1 cross KFT. And so where F1 up to Ft is a system, complete system of eigenforms for the Hecke algebra. Okay, so now I can consider, for each eigenform, I can consider the projection. So, so now let me sort of describe the Eichler-Shimura construction, which to every modular form, which to every eigenform, so what the Eichler-Shimura construction does is, given an eigenform, Fj, one of these eigenforms, it produces an abelian variety quotient. So given an eigenform Fj, it produces a quotient of J0 of P defined over the rationals, the rational quotient, abelian variety quotient of J0 of P. And how does that work? Well, you just let I sub f be the kernel of the natural projection from the Hecke algebra to the field K sub f. Okay, so you just project onto that piece in this direct product decomposition of T tensor Q. And you define A sub f to be the quotient J0 of P modulo I sub f. Okay, so this quotient of J0 of P has all kinds of wonderful properties relating its arithmetic to the modular form that was used to construct it. Okay, so what do we know? What we know about this quotient A sub f? Well, so the first thing is that we know what the Q rational endomorphisms of AF are. So it's actually isomorphic to O sub f, where O sub f is the ring generated by the Fourier coefficients, an of f. So OF is the subring of kf, the order in kf, generated by these Fourier coefficients. Well, it's actually, so how does that come about? Well, the endomorphism ring clearly contains this. That's not, because that's coming from the Hecke action. Okay? So this comes from the action of the algebra T on AF, right? On AF, which factors through the quotient T mod IF, which is identified with OF. Okay. So you have this ring of integers, or this order in a field which is acting on AF. And moreover, the dimension of AF, so this is the second fact, the dimension of this. So yeah, so this containment is clear, but then using the fact that we're working in prime level and working a little bit harder, one can actually show that this containment is inequality, although it's not terribly important for our purposes. It's really enough to know that this contains this ring. The second thing is that the dimension of AF is equal to the degree of kf over q. So what that's telling us is that this AF has a very large endomorphism ring. It has an endomorphism ring whose rank over Z, in this case, is equal to the dimension of the abelian variety, to its dimension. So what that means in particular, as a consequence of that, if I look at the Elliptic representation associated to AF, so this Elliptic representation which we introduced yesterday in the context of the proof of Falting's theorem, well, we can look at this as a module, as a vector, well, as a module, so is a module over the field KF tensored with QL. So this is just a ring, or the product of fields, right? So it's a module over this ring which has rank 2. So this is kind of generalizing the fact that if you have an elliptic curve, then its Elliptic tape module would be a two-dimensional vector space over QL, and this is a rank 2 module over this ring of field of Fourier coefficients tensored with QL. And maybe let me mention one last thing which will become important tomorrow a little bit, and when I keep this up actually. What is it? Yes? You're sort of optimal. Maybe. What do you mean by minimal? Yes. Yes. In this case, these AFs are irreducible. They're simple. Maybe this is property 0. The AFs are simple quotients. They don't break up further into irreducible pieces. Excuse me? Yes. Yes. Right. So this is another thing that, so from all this, we can see that the J naught of P, maybe I'll write it here because it's an important point, that J naught of P up to isogeny breaks up as a direct product of these A sub Fs. Which one? This one here? This one, okay. Is that okay? Yeah? Is that good? Is that good? Yeah.
So AF is simple over Q or even over C?
Yes, Q simple over Q, and in this context, even over C. Even over C. That might not always be the case, I think, for composite levels. For J0 of P, you have this simple picture. I should caution that a lot of the things I'm saying, in order to kind of simplify things, I'm only saying things for J0 of P, P a prime. it gets a little bit more complicated to describe this decomposition when I look at J0 of n and n is not a prime, okay? There's other issues. I mean, in fact, the Heck operators might not be semi-simple, but here we're just focusing on that case where I can make statements that are a little bit cleaner. So, yes, so from what was just mentioned before, so that means that J0 of P decomposes, is isogynous over Q to the product of these simple quotients, A, F, J. So now, where Fj runs over a system of eigenforms in S2 of P, Q bar. Okay, so here, I should emphasize that I'm looking at a system of eigenvalues, but I don't distinguish between two systems of eigenvalues which are conjugate under the action of gal Q bar over Q. So if I can go from one to the other, I just count these once. Okay, so this is forms in this modulo the action of gal Q bar over Q. Right? Otherwise, I'd be counting things too much. I'd be getting forms of multiplicity, factors of multiplicity. So that's what J0 of P looks like. And so now we have to understand the A sub Fs. And that is gotten via the connection with L series. So, okay, well, to any abelian variety, we can associate its Hasev A L series. So if A is an abelian variety, I define the L series associated to A as an Euler product taken over all the primes. And the other factor is 1 minus the Frobenius element at L acting on some p-adic Tate module of A, but I only take the part which is fixed under the inertia group L to the minus inverse. Okay, so this is the definition of the Hasev AL series associated to A. You can also write down a definition of these Euler factors where basically the data that you need to write down the Euler factor at the prime L just depends on the number of points of this abelian variety over the field with L elements, at least for the good primes, for the primes of good reduction. Okay? So this is a sort of arithmetically defined L series, and we know very little about it. We conjecture that it should have an analytic continuation, a functional equation, and so on, but we don't know very much a priori about this type of L series. So this is the Hasev L series of an abelian variety A. But we have another completely different kind of L series, which is associated to a modular form. So if I have an eigenform for the Heck operators, I can define the Heck L series following Hecke, which is just the L series attached to a modular form. So this is of a modular form, F, of an eigenform. So LFS is just the sum of an of f, n to the minus s, n going from 1 to infinity. So it has a definition in terms of the Fourier expansion of this modular form f. And it can also be expressed as an Euler product over the primes, 1 minus ap of f, p to the minus s plus p to the 1 minus 2s inverse, at least for the primes of good reduction. And then there's something else for the bad primes. So we have this kind of explicit formula. Now, you see that these two L series are defined in completely different ways, and the definition of this one is much more analytic, because these are just coming up as Fourier coefficients of some holomorphic function on the upper half plane satisfying nice growth properties. And in fact, this L series of Hecke is essentially a Mellin transform of the modular form. So it's obtained by a fairly simple process from the modular form. You can write it essentially as the integral from 0 to I infinity f of it, t to the s minus 1 dt, after multiplying by some gamma factors. So if you look at the L function LFS, you multiply by gamma of s, and you take in some integer, well, the P, I guess, in this case, to the S over 2, I think that this is what you need. You get that this is equal to that. Okay? So it's essentially a Mellin transform. It is, a Mellin transform of the modular form. The Mellin transform is the L series multiplied by a simple gamma factor. So, having said that now, the main point is that this Hecke L series, we know a lot about its analytic properties because of this connection with modular forms. So this was proved by Hecke, so very early in the history of this subject. So Hecke showed that these L series have functional equations and analytic continuations, which are very much the same as are expected for the Hasse-Weil L series. So Hecke shows. Maybe let me give you an exercise also. Here, I'll give you an exercise. Show this infinite product converges absolutely for the real part of S greater than 3/2. And this, you have all that you need to really tackle this exercise. What you need is that the rationality of the Elliptic representation associated to A in the sense of yesterday's lecture. It says my lecture yesterday, and so we need to know something about. Okay, so Hecke proved that LFS has an analytic continuation plus a functional equation. And the functional, okay, so in particular, we can talk about the value of this L series at S equals 1. So this makes sense, because this function extends to an entire function on the complex plane, and in particular, you can make sense of the values at points that lie outside the domain of convergence of the series used to define it. Well, you see the analytic continuation follows from this representation, which converges everywhere. Okay? So we have that. And now, let me sort of mention the big result, which connects these two types of L series in the case of the abelian variety A sub f associated to modular form. And the theorem, which is part of what was proved by Eichler-Shimura in the construction, is that the Hasse-Weil L series of the abelian variety associated to F is equal or is related to the L series of the modular form F that was used to construct it. It's actually not quite this L series, but you need to take a product over all the embeddings of Kf into the complex number. So this Kf might be an extension of finite degree of the rationals. Then you have to take all the Galois conjugate embeddings, and so you get some Euler product of larger degree. But that's what it looks like. So it's a product of these L series, which we know, thanks to Hecke, have nice analytic properties, analytic continuation, and so on. In particular, thanks to this result, we have a much tighter grip on the arithmetic of these abelian varieties, of these particular abelian varieties, because we know that their L functions have analytic continuations. And so we know that the L function of AFS has analytic continuation. This is thanks to this tight connection with so that's wonderful, because we have a conjecture, the Bertrand de Dyer conjecture, which relates the behavior of this of the Mordauvet group, which is exactly what we're interested in, to the analytic behavior of the L series at S equals 1. And so conjecture, and I'll be talking a lot more about this conjecture next week and stating a more general version, but the thing I'm interested in is that if I have an abelian variety A, then we have a criterion for A of Q to be finite. So the cardinality of A of Q is finite if and only if LA1 is non-zero. Of course, to make sense of this conjecture, you need to be able to talk about LA1. And at least for these modular abelian varieties, we're in the good situation that we at least can talk about LA1 without invoking some extra conjecture. But then, even better than that, there's a fundamental result, which is much more recent than the result of Eichler and Shimura, which is a theorem of Gros-Zagier and Kolyvagin, and which I'll be talking a lot more about next week, which tells us that, in fact, we know this part of the BSD conjecture for these so-called modular abelian varieties that come from modular forms. So the theorem is that if the L function of AF, now AF I know is non-zero, then AF of Q is finite. So that gives us a way of tackling the problem of constructing a quotient of J naught of P with finite mode L group by exploiting this connection with L series. Okay? And so now I can kind of give you, so this I'll talk about next week. I mean, this is one of the fundamental results in the subject, and so I'll be devoting some time to it in the lecture series of next week. So anyway, this allows me to give a construction of the quotient, which I promised you, this J0 sharp of P. And the construction is the following. I just look at the natural map. I take I sub, I'm going to call it I sub E to be consistent with the notations that will be used in Marussia Rebolledo's lectures. So this is going to be the kernel of the natural map from T to the product of the K sub F's, but I only pick up the ones for which the L series is non-zero. So I look at this projection of the Hecke ring, and then I define J0 sharp of P to be J0 of P modulo this ideal. So this is isogynous to the product of the A sub F's taken over all F's for which LF1 is non-zero, and therefore, by construction, J0 sharp of P of Q is finite. And in some sense, well, we expect by the BSD conjecture, by a more general version, that this is somehow the largest quotient with this property, having finite mode L group. Okay, let me just now, I'm going to just quickly finish by saying that we can kind of give a more concrete description of this ideal, IE, and therefore of the associated abelian variety quotient, which will be useful for what Marussia Rebolledo will say. So we can also define the ideal I sub E as the annihilator in the Hecke algebra of a certain element, which I'll also call E, where E is going to be an element in the homology of the modular curve x naught of P with coefficients in Q. And this element is going to be simply the one that corresponds, which is related to the path from 0 to the cusp infinity. So if I look at the upper half plane, I can look at this path from 0 to I infinity, and you see from this integral formulation, this integral representation of the L series LFS, that the special value of f(1), LF1, is essentially the integral from 0 to I infinity of the associated differential form. So this functional integrating from 0 to infinity is capturing the non-vanishing of this L series at s equals 1. So that's how you detect whether the L series doesn't vanish. So that's why, I mean, this path is not quite closed on the modular curve, so it doesn't belong to the integral homology, but if you tensor with Q, it's a result of Manin that this is actually in the rational homology. And this is the element whose annihilator we take, and this ideal is the same as that one that I wrote down more concretely, and if you take the quotient, you get what's called the Whining Quotient. So this thing, which I call J0 sharp of P, is sometimes also called the JE or JE of P, I'm not sure, and it's called the Whining Quotient. It was the quotient that was introduced by Merel to tackle sort of generalizations of Mazur's result from the case d equals 1 to a higher degree. And that's what Marussia is going to discuss now. So in the sort of second half of this lecture, so until about 3:45, I guess it's the second. Yeah, I mean, maybe she'll take an extra 10 minutes beyond the end. She'll discuss how this kind of results can be, or these ideas can be used to extend Mazur's theorem from the case of rationals to number fields of higher degree. Okay.
Guten Tag. Ich freue mich, hier zu sein. Am liebsten würde ich diese Konferenz auf Französisch halten, denn ich spreche kein Deutsch. Aber man hat mir zu Englisch geraten. So I hope it was understandable. And now I will maybe introduce my talk of tomorrow. Là? Okay. So I will talk about torsion of elliptic curves. Can I erase it? Yeah. So if you take an elliptic curve over a number field, the Merel theorem says that the group of torsion of rational points. So let E over K be an elliptic curve and K a number field. The theorem of Merel says that the group of rational points is a finite generated abelian group. And so in this talk, and the talk of tomorrow, we will be interested in the torsion part of this group. And it's a conjecture of, it's a celebrated conjecture, famous conjecture, which is called uniform boundedness conjecture, and which is due to Hogg in the 70s, and perhaps due also to other mathematicians like Poincaré around excuse me. So Poincaré maybe formulated a part of this conjecture already at the beginning of the century, and Lévy maybe in 6th. I am not sure of this date. And this conjecture says that you can bound the torsion part uniformly in the degree of the number field. So, namely, if you take d greater than 1, then there exists a bound b which depends on this degree, such that for all elliptic curve over K, a number field with degree d, then the torsion for all such elliptic curves, you have the cardinality of the torsion over K bounded by the BD. And this is since 95, this is a theorem of Merel. And the goal of my talk is to to give a sketch of a proof of this theorem. And actually, this theorem relies on several results, and in particular on Mazur's and Kameni's works. And actually, Merel showed another theorem, which I will call theorem 2. So let's call it theorem 1. And Merel showed that let P greater than something, D2, and let E be an elliptic curve over a number field with degree D over Q greater than 1. Suppose that you have a P torsion point P defined over K, so P torsion point. So here I forgot to say that P is prime. So suppose there exists such a point, then no, okay, excuse me. Let P be a prime. So let E like that. Then P is lower than D to the 3D square. So this theorem consists to bound the P torsion part of the rational points. And by a result of faultings and fray, it suffices to show the first theorem. So knowing something about the P torsion part, you can bound the torsion part in interior. And this has been proved by Mazur and Kameni. And it. Sorry, the fact that it implies the fact that the theorem 2 implies the theorem 1.
So what if all things are private?
Because they use some works of faultings and fray, and they put it in the machine to have this implication. Anyway, so tomorrow my talk will give a sketch of proof of the theorem 2. But before, I want to do some remarks. So the first one is that in this theorem, you can notice that D is strictly greater than 1. But if you take D equal 1, you have the Mazur theorem. Which has been explained by Darmon just before. So I can recall you that for P greater than 11 or P equal to 13, then Y1P has no rational point over Q. And if you look at the signification of this, it means that there is no elliptic curve defined over Q endowed with a Q rational P torsion point. So you see that to treat such a theorem, it's easier to look at modular curves which parameterize such pairs E with a point, P torsion point. And in fact, the Merel theorem relies deeply on the Mazur's method. So the second remark I want to do is that the bound t to the power 3d square is not optimal. I mean that, for instance, Oesterle improved this bound, improved the bound but in this talk I will only speak about the Merel's original proof, because the proof of Oesterle is almost the same. And I wanted also to say that, that unfortunately this the path from theorem 2 to theorem 1 is not effective. So, I mean the works of Frey and Foltings was not explicit at all. So the bound BD that you obtain in the theorem 1 is not explicit. But in 1999, I think, Pierre Parent bounded the P to the R torsion for R be an integer greater than 1. So it allowed Parent, with the theorem of Merel, to have a BD explicit, and actually it's exponential in the degree of the number field in D. And we conjecture that there is a bound BD which would be polynomial in the degree. Okay. So now I will explain why the theorem 2 is related to the Mazur's method. And tomorrow I will finish. Can I don't know. Oh, so maybe. Okay. Yes, I mean we hope so, but we don't know how to do that. It's a conjecture.
We just have a bound. Just a bound.
The global bound, not for the P torsion part. So let's suppose, so this is the first paragraph. So suppose you have an elliptic curve over a number field of degree D, greater than 1, if you want, and P, a P torsion point defined over K, then, like I said before, the pair EP defines the point which I will call, like Henri Darmon, x tilde, in the affine part of the y1p modular curve, and which is k irrational, which is defined over k. And as Darmon did, you can project this point, which is here. I mean, you can map this point on the x node p modular curve. So you take x tilde here, and so this corresponds to EP, and you can map this point, forgetting the point here and taking only the group generated by this point. And you obtain a point which is k-rational, because this map is k-rational. But now if you take sigma 1, sigma d, the embeddings of k into C, and if you look at sigma 1 x, sigma d x, like this, you obtain a point of the d-symmetric part, d-symmetric power. So of x0p. So what is it? It's a quotient scheme. So if you take the d power of x0p, you can I mean, the symmetric group sigma d acts on the d-tuple of this modular curve, and you take the quotient. So this is a scheme which is smooth over z, where z is, like in the Darmon stock, z of 1 over p. And since if you look at the Galois action on this d-tuple, it's only permute each coordinate. So if you take the quotient by the symmetric group, you obtain a point which is rational over Q. Okay, you can take the Galois closure of it, and it's the same. So you see, now the method will be almost the same as in the case d equal 1, because sorry?
It's equal to x sigma, x in y1 but we discussed only x.
Okay, but I am not sure if I have understood your question. So you take, is it your question? So it includes like, and you are right. Here it's included in the affine part also. So now you are reduced to use this curve, and the point is that you will do the same as in the Darmon stock. You will look at the map like this, which maps a point, a d-tuple Q1 QD, on the divisor Q1 plus QD minus D infinity. And you will take the good quotient that just introduced Darmon, which is the so-called Whining Quotient. So let's denote it by phi e d. And the theorem says that so it's a theorem of Mather extended by Kamieni's work, which says that if phi e d is a formal immersion at the point infinity d, which is equal to the image of infinity in the quotient. So if phi e d is a formal immersion at infinity d, since this is a good quotient, then y1 p of k is empty for all number field k of degree d over q. So the proof of this theorem is almost the same as in the talk of Darmon. Maybe I will end here for today and explain. So, just a minute. Okay, so now you see that the crucial point is to have a formal immersion at infinity d. So we need a criterion of a formal immersion. Showed that the criterion of Kamieni and Mather is true. And it will involve modular symbols and some things. So there is a suspense till tomorrow. Okay, thank you.